Hello friends, this is part 2 of question paper solution physics C1 paper of first semester Dibrugarh University BSc first semester. Okay, and this is the paper of 2023, and this is my Insta ID. If you want to follow me, you can follow me ozalekazit123. Right, so before we start, please subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you. Okay, so now let's start. So today we are to start from question number 2. We have already solved question number 1 MCQ problems. So link is in the description box of part 1, okay, where you're gonna get the answers of question number 1. Okay, now question number 2a. What is Galilean transformation? Explain it by taking an example. Okay, so now let me answer this question. Okay, so let me take a new slide to answer this question. So let us assume, suppose we have a frame of reference. This is suppose S dash, which is moving with a velocity v with respect to another frame of reference, that is S. Okay, that is S. Its origin is O, and the origin of S dash is suppose O dash. Suppose we have a point here. That point is suppose P. And position vector of this point, just wait, let me write it properly. O dash is the origin of S dash. Okay, so the position vector of this point P with respect to the origin O is suppose vector R, and the position vector of P with respect to the origin O dash is suppose R dash vector. Okay, let me assume that way. Now you see, so here, so let us consider that at time t is equal to 0, at time t is equal to 0, O and O dash were the same, but after t seconds, separation between them. Now you see, let me consider this way. This is one frame, and this is one frame which is S, and this is the origin O here, and the another frame is also at the same position when t is equal to 0, which is S dash, and O dash is also here, both coincides. After time t seconds, this S dash move forward and O dash comes here, and this separation will be given by, if it is moving with velocity v, then this separation will be given by v into t, right? V into t. So we can say separation between them is v into t, right? V into t. So that's why we can write separation between them, here you see, will be R vector minus R dash vector, that will be equal to V into T, right? V into T. So I have considered this is moving along x-axis. Okay, I have considered that way only. So then this separation will be given along along x-axis. So y and z suppose remain same, then we can say, or we can write that x is equal to x minus x dash is equal to v into t, and y and y dash is equal to both same, suppose, right? If the position with respect to s, if we consider x comma y comma z, and if the coordinate of P with respect to S dash, if we consider X dash, Y dash and Z dash, in that case y dash remains same, z dash remains same, but only X coordinate is being changed because it is moving along x-axis, if we consider that way. Okay, so instead of writing all these three equations, I have represented using this, okay, in vector form. So, and here if you differentiate this equation with respect to time, both sides, okay, so then you're gonna have second order derivative of r dash minus, second order derivative of r and r dash is equal to 0. Here this equation number 1 is called equation 1 is called Galilean transformation, this is called Galilean transformation. Okay, so now let's move on to the next question. So now our next question is 2b, what is work energy theorem? So let me explain work energy theorem. So according to the work energy theorem, the change in kinetic energy of a particle is equal to the work done on it by a net force. This is called work energy theorem. Okay, so now you see what does it mean actually. Suppose we have an object here, right, and suppose it has initial velocity u, let me consider that way, and I have applied a force F, and its velocity increases to v, right. Then the work done by this force will be given by, if its mass is m, suppose, will be given by work done by F is given by the final kinetic energy, that's going to be half m v square minus initial kinetic energy half m u square, right. So change in kinetic energy gives the work done by this force. So let me write it properly, just let me clean this. Okay. Suppose an object of mass m be moving with velocity u, and its velocity increases to v due to an application of force F, then the work done by the applied force is W is equal to change in kinetic energy, there is final kinetic energy minus initial kinetic energy. So final, that's going to be half into mass into final velocity square, and minus half into mass into initial velocity, square of initial velocity. So this is all about work energy theorem, right? So hope you have understood this. So now you see, state the physical significance of moment of inertia. So what is the physical significance of moment of inertia? So now let me write the answer to question number 2C. So let me answer this question. So we know that kinetic energy, the kinetic energy of a body in linear motion or translational motion, just wait, or translational motion is given by half mv square, where m is equal to mass of the body moving with velocity v, right? Moving with velocity v, and the kinetic energy, which is kinetic energy of a body, kinetic energy of a body let me write rotating body, or you can write energy of a body rotating with angular velocity omega is given by half I omega square, where I is the moment of inertia of the body, right? Where I is the moment of inertia of the body, right? Now you see, if you compare these two equations, then you can see this is 1 and this is 2. Comparing comparing 1 and 2, we can say this moment of inertia in rotation plays the same role as mass plays in translational motion, right? It plays the role of mass, okay? Moment of inertia plays the mass, role of mass in case of rotational motion, because this is, you see, half mv square, this is linear velocity, and this is half I omega square, this is angular velocity. These two are velocities, right? And this is mass and this is moment of inertia. That means mass and moment of inertia plays the same role in these two situations, in case of linear motion and in case of rotational motion. The mass, moment of inertia plays the role of mass, okay? Plays the role of mass in case of rotational motion, right? So what we can say here, comparing 1 and 2, we can write that in rotation from pairing 1 and 2 we get in rotation the moment of inertia plays a similar role as mass does in linear motion or translation motion. Right, so hope you have understood this. So this is the physical significance of moment of inertia, and or you can say that moment of inertia is the analog of mass. Okay, so now let's move on to the next question. What is damped vibration? Okay, so let me clean this and let me write the answer. So take the screenshot. Okay, so question number 2D, there are two questions, either you need to answer this or this one. First let me answer this one. So what is damped vibration? Okay, so now you see, suppose we have a simple pendulum, okay, and it is swinging both ways like this, left and right, swinging this way. Now you see, because you see the presence of air, and when it swings towards left and right, this air provides resistance. Okay, so that's why after suppose it is swinging towards left and again towards right, left, and so on, right? But due to this air resistance, the amplitude of swing decreases continuously. Suppose initially this is the amplitude, in the next time it will be shorter. This will be decreased a little bit, then again next swing, then again its amplitude will be decreased more, okay, and so on. This type of vibration is called damped vibrations. Okay, so now just let me clean, let me write the answer here. So in actual practice, when the simple pendulum vibrates in air, there are frictional forces and consequently energy is dissipated in its vibration the amplitude of swing decreases continuously with time and finally the oscillations die out. Okay, such vibrations are called damped vibrations. Right? Damped vibrations, or you can simply say that if amplitude decreases completely of a vibrating body, then such kind of vibrations are called damped vibration. But here, as 2 marks is given, so that's why I have written the answer this way. Okay, and you can add one more thing: the dissipated energy appears as heat either within the system itself or in the surrounding. Right, or in the surrounding. Okay, and this dissipated energy is proportional to velocity of the particle. You can write just wait. Velocity of the particle. Okay, so hope you have understood this. Now let me answer this question. Just pause the video and note the answer. Okay, so now let me clean this and let me write the answer of this because there are 2 questions, this one or this one, right? So we have answered this question. Now let us answer this question: what is the sharpness of resonance? Okay, now let me clean this part. Question number 2D or. Okay, answer. So sharpness of resonance, the sharpness of resonance refers to the rate of fall of amplitude which the change in the driving force driving frequency on either side of the resonant frequency So now let me explain. Suppose here, so this is 2 marks question. Let me draw a graph. Now you see, so this axis represents frequency and the vertical one represents amplitude. Okay. Now suppose to understand this, first we must know what is resonance. Okay, just let me write it properly. Just wait. So now let me explain what is resonance. Now you say, suppose we have a simple pendulum. If you just bring the bow here at this position and if you just release, and it will oscillate this way, right, with its natural frequency. That means if you bring the bob at this position and if you release it, so it will oscillate with a frequency. That frequency is called the natural frequency of this pendulum. Now you see, if you want to, if you apply a force, external force to continue this oscillation, then the frequency of the force that you have applied, which is called driving force, and frequency of that driving force is called driving frequency. So let the driving frequency be suppose P, and the natural frequency of this oscillation be suppose omega naught. Okay, now you see, if the frequency of your driving force is very close to omega naught, or you can say this way, the amplitude of this oscillation of this pendulum will increase as the driving frequency approaches to the natural frequency of the simple pendulum. Okay, when P is equal to omega naught, then it's gonna attain the maximum amplitude. Okay, right, and that phenomena is called resonance. Okay, so now you see, if you draw the graph, okay, if you draw the graph, right, so of here you see, now you see, if you draw the graph of amplitude versus frequency, so let me tell you one more thing. This is the natural frequency, suppose omega naught, and frequency of the driving force is suppose P. In case of damped oscillation, right, if there exists damping force, So it depends when you are gonna have the maximum amplitude. So it is not necessary that you're gonna have the maximum amplitude when P is equal to omega naught. It depends on the damping force. If the damping is very small, then you're gonna get the resonant frequency nearly equal to omega, not exactly. Okay, so you're gonna get such kind of graph. So this is for small damping. So you're gonna get maximum amplitude when P is almost equal to omega naught. Okay, when P is almost equal to omega naught for small damping. For small damping, right? And for large damping, so let me use another ink. Then the maximum amplitude peak, this peak will shift towards left, little bit left, in case of maximum damping, right? A large damping, in case of large damping. For large damping, just wait. This is for large damping. For large damping, right? For large damping. So you must draw the graph, and where P is the driving frequency, and omega naught is the natural frequency. Right. So now this answer is completed. Now let's go to the next question, 2E. What is Coriolis force? Under what condition this force is maximum? Okay, so let's answer this. Let me clean this first. Pause the video and note it down. Let us suppose we have two frame of references in space. Let me show you now. So this is one with origin O, and this is x-axis, y-axis, and z-axis, right? So let me take another frame of reference, just wait. And another frame is x, this is x dash, this is y dash, and this is z dash. Okay, and origin is the same. Okay, and unit vector along x-axis is suppose I cap, along y-axis j cap, and along z-axis k cap, and the unit vectors along x dash is suppose I dash cap, then along y dash cap is y dash is z dash cap, and along z dash is suppose k dash cap, right? So let me take that way. Suppose we have a point P here, and its position vector is suppose r. So here is the position vector of P, suppose r vector, right? So let us consider two systems S and S dash. Their origins coincide at O, right? And this S dash is in uniform rotation relative to S with angular velocity omega, okay, with respect to S, and a particle of mass m is at P. X, y, z is the coordinate in the system S, right? And its coordinate at S dash is this, right? So we have considered this one. So that's why we have got the position vector in S and S dash. These were the position vectors, right? So now you see, then the force on the particle on the particle in the system S dash is given by the expression, just wait, this is the expression of the force, okay. Here you see, in this expression, that capital F is the force, F dash is the force acting on the particle P in the S dash, and F is the force on the particle in S. Okay, and d dash r by dt, this represents velocity of the particle with respect to S dash, and this term here, this term is Coriolis force. Okay, so hope you have understood this. Let me explain again. Just wait. So here we have considered two systems. One is this x coordinate, y coordinate, z coordinate here for one system. This is the S system, and another is in S dash system. The axes are x dash, y dash, and z dash. Okay, and in these two systems, S and S dash, the position vector of the particle of mass m respectively are this. These are the position vectors in these two frames. Okay, S and S dash. So hope you have understood this. So then the force, now you see, as these two systems are in relative motions, okay, so relative to these two systems, the force acting on it will be different. So here in the system S dash, the force F dash is given by this expression, where this term represents Coriolis force, and d dash r vector, derivative of r vector with respect to t, this d dash r by dt is nothing but velocity of the particle in the S dash system, right? So hope you have understood this. This is what all about Coriolis force. Okay, so now you see, let me go to the next question. Actually not next question, same question, question number 2e, but there are two questions, right? So we have solved this one. Okay, one more thing, under what condition this Coriolis force is maximum, that has to be written here. I forgot to mention. Just let me go to the new slide, okay, to give you this answer. What is the condition? Okay. So here you see, just let me take it and let me go to the next slide. So here is the Coriolis force, expression for Coriolis force, right? This is the Coriolis force. So here we have negative sign in this expression, so as it is a vector quantity, so let's put here minus. So this is minus here. Now you see, this cross product of vectors, so we can write 2m omega into derivative of r with respect to t sine n cap. N cap is the unit vector which gives the direction of Coriolis force, right? So n is the unit vector perpendicular to both omega and v dash, right? That means v dash means here d dash r by dt. Okay, that's it. So now you see, when sorry, let me write one more thing. There should be a theta. Okay, this should be theta. Now let me write one more thing. Theta be the angle between omega and v dash, right? So we know that maximum value of sine is 1, right? For Coriolis force to be maximum, sine theta must be equal to 1, right? If that is the case, then we know that sine 90 is 1, right? So therefore theta must be 90. Okay, so this is the condition for Coriolis force to be maximum, right? So just you must mention these things. What is theta? Okay, right? And you have to mention this expression as well, right? So now let's move on to the next question. Here one more thing, let me go back to the previous slide. Here you see we have another question. Either we need to solve this one or this one. Cyclones are not found to occur on the equator. Why? We need to give the region. Okay, so let me explain. So let me clean these things first. So now you see, let me explain this answer first, and then I'm going to give you the answer. First let me explain. Now you see, suppose this is the arc and this is the equator, okay, and we know this arc spins in this direction. This is the west and this is the east, and this is the north and this is the south, right, in this direction. Now you see, if this is the axis of rotation, now you see, so let us consider a point here near the pole and one point at equator, and if it is spinning like this, the arc is spinning like this, right? Now you can see the point at equator covers large distance compared to the distance covered by the point which is at the polar region near the pole, right? At the same interval of time. So that's why this point is moving faster than this one. Okay, this is faster and this is slower, right? So that's why now you see, we can say the point on the equatorial line is moving faster and point near the pole is moving slower. Now you see, if you imagine like this, suppose there are two cars, this is A and this is B. B is moving faster. At the moment when B cross A, if you want to throw something towards A, it's supposed to go towards A, but due to inertia it will move towards this because this one is faster, right? Similarly, if someone from A want to throw towards B, as B is faster, so it's gonna lag behind B, right? So this kind of effect occurs here, okay? So now you see, similarly, because of the same region, same kind of effect will occur, right? Let me make it black. Okay, let me make it black and let us keep it red. Okay, so now you see, same kind of effect will be occur below the equator, right? Below the equator. So let me use here the red. This effect, because of this effect, this is called Coriolis effect, cyclones are formed at the northern and southern hemisphere, right? So because of these two forces, here you see, one is in this direction, another is in this direction, so there will be a rotation in anti-clockwise direction. That's why cyclones are formed. So here direction is anti-clockwise if you see the figure, but here in this hemisphere, so if you observe this arrow, because of this, the direction will be in the clockwise direction. Sorry, that's supposed to be in this direction. This is clockwise direction. Here arrow should be this way. So this is, just wait here, just wait, let me draw it properly. So here you see, in this case, you see, because of this force, the direction should be this way. Because of this force, this should be the direction. So this is anti-clockwise, this is anti-clockwise, and here is clockwise. This is clockwise and this is anti-clockwise, right? So that's why at the equator, what will happen? This effect becomes weaker when you comes close to the equator. Okay. When you go from the equator towards the pole, this effect, Coriolis effect, occurs more effectively, right? So, and because of these two directions which are opposite, so that's why when these two comes closer to the equator, they cancel each other, you can say like that. Okay, so that's why Coriolis effect becomes weak at the equator. That's why cyclones are not found to occur at the equator. So now let me give you the answer. Just wait, let me clean this. Answer to the question 2E or. So first part of this question is done. This one, what is Coriolis force, under what condition it will be maximum, that is done. Now let us answer this part or this part. Okay, so let me write the answer. So this is the answer to question number 2E or answer. This is the answer, you can write this one. Okay, so now let's move on to the next question. So now you see we have solved question number 2E. Now let's move on to question number 2F. So what is length contraction? So I have already made videos on this topic. If you check the playlist of classical mechanics, you're gonna get there. But I'm gonna give you the link in the description box. So I'm gonna I'm gonna give you the link this way, question number 2F, and the link will be here, and you can just click the link and you can watch the video. Okay, and I have made videos on what are the postulates of special theory of relativity, so that will be also in the description box. Okay, now let's come to this point, what is mass energy equivalence in relativity. Okay, proof of this equation also given, but let me give you the answer for 2 marks question. Okay, 2G or, that is mass energy equivalence in relativity mass energy equivalence in relativity. Okay, so this is the answer to this question, question 2Z or this part. What is the mass energy equivalence in relativity, right? So this is the answer to that question. Okay, and this is the Einstein's mass energy equation, E equal to mc square, where E is the energy, m is the mass, c is the speed of light, right? So now let's move on to the next question. So here in the next question, so it is asked twin paradox. Okay, what is twin paradox? So you're gonna understand this if you know the concept of time dilation. Okay, so this is about the twin paradox. This is the answer, you can write. Okay, I have written here. I'm not going to explain this in details. First, I would like to suggest that go to the playlist and check the topic time dilation, and if you watch that, then you're going to understand this. Okay, so in this just let me tell you a little bit. Okay, in this twin paradox, here you see in twin paradox, here you see, suppose this is the earth and A and B, they are twins brothers, A and B. So B is traveling with a speed which is very close to the light. Okay, he is traveling to another planet in the space, suppose, with the speed of with a speed which is close to light but less than light, suppose. Let me consider that way. So here when B will come back and when he will reach the earth, then B will find that he is younger than A, so A will be older. Okay, so that is all about this, but you're gonna understand this phenomenon if you know the time dilation. So I have given the link of the video where I have explained about time dilation in the description box. So go to the description box and click the link to get access to that video. Okay, so now let's move on to the next question. So here, so that the kinetic energy E of a body is rotating about an axis is half of its moment of inertia. Actually, kinetic energy of a rotating body is half, I omega square. This is not half of moment of inertia, half of moment of inertia, half of the product of moment of inertia and angular square of the angular velocity. Okay, so I think you are asked to prove this one. Okay, prove this one. So E is not equal to half of I. E is equal to half I omega square. Okay, so I think there must be some must be a mistake. Okay, so let me explain it. Okay, how to answer this. Just wait. So let us consider a body which is rotating about this axis. Suppose let us consider a body. Okay, this is the body. This is rotating about this axis with angular velocity omega. Okay. So this is the axis of rotation. This is the axis of rotation. Okay, so then each particle of this body will be moving in a circular path like this, right, about this axis, right. So this is a particle, suppose. Let me consider. So this is a particle, suppose. Let me consider here. This is one particle which is at a distance Ri. Just wait, let me write it properly. This is one particle of this body. This is suppose ith particle. Let me consider that ith particle, and distance from the axis of rotation is suppose Ri. So let me take this radius as Ri. Okay, for the ith particle, and it is so if this body is moving in about this axis in with angular velocity omega, then this ith particle that I have taken here, it must be moving in a circular path. So not only this particle, all the particle of this body. Okay, so let me take that way. So now, so which question we are doing here? 2I. Answer 2I. Let us consider a rotating body, or a body rotating with angular speed omega about an axis okay, then each particle of the body must be moving in a circular path. Right. So we know that if a particle is moving in a circular path with radius r, circular path of radius r with angular velocity omega, then its linear velocity v is equal to given by omega into r, right? We know that. So let us consider so the ith particle, the linear velocity of ith particle of the body is vi is equal to omega ri, where ri is the distance of the particle from the axis of rotation, right? Let me consider that way. So hope you have understood this. Then kinetic energy of the particle, of the ith particle is Ke is equal to, let me write here Ki to represent the kinetic energy of ith particle. So that's going to be half mvi square, okay, where m is the mass of let me write here mi. This is the mass of the ith particle. Mi is the mass of the ith particle. Mass of the ith particle. Right. So this is the kinetic energy. Okay. So now let me take this as equation number 1. Then using it here in this equation, what are we going to get? Ki is equal to, if you use this equation here, that means if you replace vi by omega ri, then you're going to have half m I omega ri. This must be square of omega ri, right? So you're gonna get this. So this is, suppose let me copy this equation and let me go to a new slide. Okay. Just pause the video and note it down. Let me go to the next slide. So here is the last expression we have got, right? So therefore kinetic energy of the body can be obtained by adding the kinetic energies of all the individuals' bodies, right? So therefore kinetic energy, here you see, so I have taken here a rigid body, right? So how to find the kinetic energy of this rigid body? If you add the kinetic energies of all the particles, then you're gonna get the total kinetic energy of this body, right? So therefore kinetic energy of the body must be the sum of kinetic energies of all the particles of the body. So that can be expressed by Ke, kinetic energy, that is kinetic energy equal to summation I is equal to 1 to, suppose if there are n number of particles, then it will be given by m omega square ri square, right? So this can be written as omega square into ri square, right? So I have done that. So this is the kinetic energy of one particle. So kinetic energy of n particles will be given by this expression, omega square ri square. So where n is the number of particles of the body, right? So hope you have understood this. Now you see, just wait. So I have missed this half. Okay, you have to add all the so to get this kinetic energy. So I have we must add all the kinetic energies of all particles. M1 omega r1 square omega square r1 square plus half m2 omega square r2 square and so on. If there are n number of particles, half mn omega square rn square. Okay, this can be expressed as this, right? So hope you have understood this. So now let me clear this. Okay, now you see how here if a rigid body is rotating with angular velocity omega, then angular velocity of each particle must be same. Okay, so that's why we can write this we can keep this one out of the summation because it is constant part here. So I is equal to 1 mi square n into omega square. So this part is nothing but moment of inertia of the body. Okay, so by definition, what we're going to get, by definition, moment of inertia of the body I is equal to summation I is equal to 1 to n mi ri square. Okay, so this is kinetic energy. So this is suppose equation number. So what was the last equation number? 1. So let me take this is 2 and this is 3 from 2 and 3. So let me go to the new slide. So here you see we can replace this part by I, right? So we can write from 2 and 3. From 2 and 3 we get kinetic energy is equal to half I omega square. That's what we have got. Now you see, let me go back to the question. Here it is given that so that the kinetic energy E of a rotating body about an axis is half of its moment of inertia. Actually it is not half of its moment of inertia, it is half of its moment of inertia into its square of its angular velocity. So you can write you can show it half of moment of inertia if the body is rotating at the rate of omega is equal to 1 radian per second. Okay, 1 radian per second, then kinetic energy will be half of I. If you replace this omega by 1, then you're gonna get that. So hope you have understood this. So now let's solve the next question. Just wait. So what is the next question? Let me clean this part first. So now let me answer this question 2J. Okay, so here we need to find the differential equation. We need to deduce the differential equation of simple harmonic motion. Okay, simple harmonic motion, differential equation of simple harmonic motion. Okay, 2J, here is the answer. So we know that for a particle vibrating in simple harmonically, okay, or so for a particle in simple harmonic motion, the displacement, the general equation of the general equation of displacement is given by y is equal to a sine omega t plus alpha, right? So here A is the amplitude, okay, and this epsilon is the is epoch or initial phase, or you can say epoch, okay. And if you differentiate this equation, so this is equation number 1, let me say this is equation number 1, differentiating equation 1 with respect to time t, then you're going to have dy by dt, that gives you the velocity, right? Differentiate it, amplitude is constant, that's going to be outside the derivative, and ddx of sine x is cos x, right? Here instead of x we have this. If you differentiate it with respect to x, you're going to have cos omega t plus alpha. Then again this is function of function. If you differentiate this part which is within bracket, then you're going to have omega, right? So we can write it like this, just wait. So we can write the omega here, right? We can write this way. So hope you have understood this. This is suppose equation number 2, right? Now if you differentiate it again differentiating with respect to t, then you're going to have second order derivative of y with respect to time t, and a omega square, derivative of cos is minus sine omega t plus alpha. Here square omega square, because here you see if you differentiate this you should get minus sine omega t plus alpha, then derivative of this part, that is omega, so that's why it becomes omega square. There is already one omega there, right? So hope you have understood this. So now here you see, so this is what we have got. Now from here you can see this part into A, that is nothing but y, okay, that is nothing but y. So from equation number 1, let me rearrange these things. So here you see, we can write this way, minus omega square a sine omega t plus alpha. So we have got this part is nothing but equal to y. So that's why we can write, just wait, give me a second, just let me write it properly. Second order derivative, okay. So second order derivative of y with respect to t is equal to minus omega square into y from 1, or using 1. So this part is replaced by y. So hope you have understood this, right? So now let me copy this equation, let me go to the next page, okay, next slide. So here is the new slide. So this is the last table we have got, and if you simplify this, then you will have the second order derivative of y with respect to time t, and if you bring this to this side, then you're gonna get, just do it, plus omega square y is equal to 0. That's what we're gonna have. So this is the required differential equation. So this is the differential equation of simple harmonic motion, right? So hope you have understood. So now let me go back to the question. So here one more part. So either we need to solve this or we need to answer this one, so that kinetic energy of a harmonic oscillator is this. Actually here you see the kinetic energy of harmonic oscillator is not this one. This is average energy, actually total energy, kinetic energy plus potential energy. This will be kinetic energy at particular position, okay, not for the entire motion. Okay, so now, so in order to answer this question, I'm going to use this answer that I have already given for this. So here just amplitude is R, so let me use the amplitude, change the amplitude here. Let me make it R instead of A. So you're gonna use this same answer. Let me show you how. Just replace the A. Okay. Yes. Now you see. So now we are solving 2J, or let us consider that the initial phase is 0. In this case, let us consider initial phase is 0. Let it be 0. Then here I have to make changes here. For simplicity, we have taken the initial phase is suppose 0. Okay. In that case, this equation number 1 becomes y is equal to r sine omega t. Okay. So here we can write this equation as cos omega t. Okay, this is going to be cos omega t, right? So here it's going to be sine omega t, right? I'm going to write here sine omega t. Okay, so we're going to get this, right? So now what we can do here, you see, so here we don't need this part. Just let me cut it. Okay, just do one thing. Here you can see, just let me get more space here. Okay, so from this equation we can write that sine omega t is equal to y by r. So this is suppose equation number 2, right? Now here dy by dt is nothing but v. Okay, r omega cos omega t can be written as 1 minus root over 1 minus sine square omega t. That's what we can write. So if we use this equation number 2 instead of sine omega t, what we can put, so v is equal to r omega root over 1 minus y by r whole square. And if you simplify this, then what you're gonna get, so let me write here using 2. Now let me take a new slide. So here is the last step we have got. If you simplify this, then you're gonna get root over r square minus y square by r square, and that's going to be equal to r into omega root over r square minus y square by r, and this 2r cancels, so v is equal to omega root over r square minus y square. That's what we're going to have. So therefore kinetic energy that is half m v square, so we can replace the v by this value, right? So half m, instead of v we can write omega root over r square minus y square whole square, right? So where m is the mass of the particle in simple harmonic motion, right? So therefore kinetic energy k, that's going to be equal to half m omega square r square minus y square. That's what we have got. So this is suppose equation number 2. Now let's find potential energy. Okay. Potential energy, so let me represent it by U. Okay. So in order to obtain the potential energy, first you see, just let me write here, from the differential equation of simple harmonic motion, we got second order derivative of y with respect to t plus omega square y is equal to 0. That's what we have got, right? So this implies this minus omega square y. So second order derivative of y is nothing but acceleration. Therefore acceleration, this is nothing but acceleration. So in case of simple harmonic motion, acceleration is negative, right? So therefore magnitude of the force on the particle, therefore the force on the particle, mass into acceleration, so mass into acceleration, so this is the magnitude of the force, right? So if this is the force, then potential energy can be obtained by integrating from 0 to y by integrating m omega square y dy, right? So that is the work done by this force, okay? Work done by this force, that's going to be stored as potential energy, right? So now you see, if you integrate it, then what you're gonna have, so here this part is constant part, so that's gonna be taken out of the integral. So integrating y, you're gonna get y square by 2, and we have to integrate it from 0 to y, and doing so what we're gonna have potential energy is equal to half m omega square y square. Therefore total energy is equal to k plus u. So let me copy this. So let me go to a new slide. So here, so we have got kinetic energy from the previous slide. What we have got, this is the kinetic energy in equation number 2. Here you can see kinetic energy. This is the kinetic energy expression, right? And the potential energy is this. Here you can see u is equal to this one. This is the potential energy we have got, right? So if you use here half m omega square plus this plus half m omega square y square, that's what we're gonna have. So if you take half omega square common, then within bracket we're gonna have r square minus y square plus y square, so that's gonna be equal to half m omega square r square. This is the total energy of a particle in simple harmonic motion, and kinetic energy will be half m omega square r square when it is possible, when y is equal to 0. For y is equal to 0 only, kinetic energy of the particle in simple harmonic motion will be equal to half m omega square r square, right? So hope you have understood this. So in the next video we're going to solve from question number 3, okay? So thank you for watching. See you in the next video. Do subscribe to the channel, hit the thumbs up button if you like my videos, then also share with your friends, okay?